So we've seen that all of the linear motion variables that we have their analogs in rotational motion. We have position, angular position, velocity, angular velocity, acceleration, angular acceleration, and we have analogs for the other quantities as well. Force has its analog in torque. Mass has its analog in moment of inertia. Back in chapter 4, we introduced Newton's second law. Newton's second law was A equals F over m. The acceleration is equal to the force divided by the mass. We want you to come up with a version for Newton's second law for rotation. And what should it be? We'll give you some choices. And in fact, Newton's second law for rotation is exactly analogous to Newton's second law. A equals F over m turns into alpha, angular acceleration, equals torque, tau, divided not by mass, but by moment of inertia, I. Alpha equals tau over I. So, if I want a wheel to accelerate, I have to provide a torque, and I have to know the wheel's moment of inertia to determine how big is the angular acceleration. And that's an example of the type of problem you're going to see in chapter 7. I have a pencil, and I try to balance it on my fingertip. It's actually quite difficult. It's quite difficult. I really can't learn to do this. But on the other hand, I have a very, very large pencil that's identical to the smaller pencil. It's just larger in every dimension. It turns out this is quite easy to balance on your fingertip. Quite straightforward to balance this on my fingertip. And it turns out this is a rotational motion problem. Because when I'm balancing it, what happens is this. The pencil starts to tip. I need to have time to get under it to be able to keep it balanced. So here's what happens. It starts to tip. Will I have time to get there? Well, if I have a big pencil, here's what happens. The center of gravity is right about here. It tips to the side. There's a downward force that acts here. The weight force acts at the center of gravity and produces a gravitational torque that causes this pencil to rotate. And it turns out the angular acceleration that's produced by that torque on something of this size with this moment of inertia is inversely proportional to the length of the pencil. So if I have a short pencil, it's not going to happen. But this one's 10 times longer. If it's 10 times longer, I have 10 times as much time to get under it. And that is plenty of time to learn to balance it. And that's the solution to the baseball bat problem we talked about last time. The center of gravity of the baseball bat is near the end, and we can tell that by looking for a balance point. It's out here near the fat part of the bat. So if I put the bat this way, the center of gravity is very, very high. The balance is easy. If I put the bat this way, the center of gravity is lower. It's going to rotate much more quickly, and that is a much trickier problem to be able to balance it. These are actually rotational motion problems, and they're the type of problem you look at in Chapter 7. Now in Chapter 8, we're going to keep the concept of torque because we want to look at forces on distributed objects, and we're going to look at problems with Newton's second law with torques that act on objects where the acceleration is zero. We're going to look at something called statics.